So this is about finite state machines. A finite state machine takes, as its input, basically how you create one is you draw out your finite state or your state transition diagram or diagrams, figure out what all your states are, what has to happen for each, and then you write a little program that deals with that. You can find lots of programs out there for lots of languages on how to make a finite state machine. There's libraries and all that. I didn't find anything great for C, so I combined a few things that I found that and cobbled together something that I like. It's simple. There could be improvements made to it, but they probably aren't worth it, to be honest. So let's take a look to start with. So we have this concept of an environment struct. This is a forward declaration, so we don't know what the struct looks like yet. That may actually, that actually isn't needed anymore. I can just do this. And there's various ways to do structs. Sometimes we'll do the type def like this. So the environment, it has two variables in it: the state you're coming from and the state you're in. It's basically there because it can't make an empty struct. I don't think that's legal. Maybe it is. But these are sensible things to have in here. This is going to use the polymorphism idea from last term. So this is a parent class, essentially, and we'll have other structs that derive from it. And remember, all we need to do for that, you'll see it in another part of it, but that struct just has to have one of these structs as its first element, and then it can directly access these. But we'll see that later on. Then there's this handy type def for a function pointer. It's a state func. So every time you change states, you call one of these functions. It takes an environment pointer, and it returns an int, which is the next state to go to. And then we have this thing, state transition, which you'll see it laid out quite nicely. It's got, call it from and to. Let's change that. I want to be consistent, so we'll call it from ID and the to ID. I'll have to update some more code. So we're moving from this state to this state, and this is a function we're going to call when that happens. And then we just have this one function. It's no return, which means it never returns. And it is finite state machine run. It takes an environment pointer, right? This thing here. We're moving from this state to this state. And here's the list of all the transitions that we can make. So that's the interface of it. I'm going to show you how you use it, and then we'll go into the implementation of it. Please remember, this is a way to implement it. There's no single right way. So here's our environment. I could not think of a good name, so I just called it the environment. But you'll notice that the very first element is not a pointer to, it's just the actual struct. So that means that when we have memory for this, the first part of the memory are these two values, and we can just access them directly. And then we have this Boolean, which is just A or B, and we'll come into that later. I'll also, before we finish the video, go back and re-explain how I might do this for an HTTP server, something you're familiar with. So then we have our main. It's got the environment, and it's got all of the transitions. So these transitions are pretty simple, and these are the defines up here. So we can move from the init to the start. And when we do that, we're going to call the start function. Start can either return A or B. If start returns A, it'll call the A function. If start returns B, it'll call the B function. If start returns an error, it'll call the terminate function. A can call end, or A can move to the state of end, or A can move to the state of error. B can move to end, or B can move to error, and then we just have to finalize our list here. These values actually don't matter. The only one is here, because what we're going to wind up doing is looping through this structure later on, or this array later on, and we're going to stop when we hit null. So none of these functions can be null. Important to note that. Then we grab the environment. We need to use a pointer. We can't just use the environment. Actually, is that true? I don't think we actually do need to do that. I think we can just actually do this. Look at me making things simpler. So we can just use it as a local variable, no malloc needed. So we're going to run the thing, and we're going to say move from the initial state to the start state. So that just is a primer, because the first thing this does is figure out what state to get into. So init would be like turning on the toaster, and start would be, okay, this toaster is sitting there waiting for you to do something. So when we do that, we're going to call this start function. The start function takes an environment, and it comes in here. It just prints out some information about we're moving from this state to the, this should be start. So we're going to start in the start state. We're moving from init to start. Those are the IDs. Those would be init and start here. So it's just information, so we have it. We cast the environment pointer to the environment pointer, so we can access the A or B. If we didn't do that, all we'd have access to is this part. So then we can check to see. So if we passed in true, it's going to return A. Otherwise, it's going to return B. So if we passed in false, it'll return B. So this state can result in one of two other states being gone to. So then what's going to happen inside of this run thing is it's going to figure out, okay, start has returned, it returned A. We were moving from start, now we're moving to A, or it returned B, right? In this case, since that's true, it's going to move to A. So it'll basically just iterate over this until looking, no, is this start? No, it's not. This is start, yes. Is this A? Yes. Okay, that's, then we're going to call this function. We're going to call the A function. So the A function just prints the stuff out and says, I want to move to the end state now. So it'll loop through here. Are you A? No. Are you A? No. Are you A? No. Are you A? No. Are you A? Yes. Are you end? Yes. Okay, we're going to call the end function. And the end function is also no return because it calls exit. And it exits out of the whole program. If at any point in time there's an error, it calls the terminate function, which exits with a failure. Things to note here. This takes an environment. Say A and B wanted to set different exit codes, so we're not always doing exit success. We can do that just by adding another variable inside of our environment, like int exit code. And here we could say env2.exit code is assigned 1, or we'll make it 10. And otherwise we'll make it 11. And then in the exit, we're not going to return exit success. We're going to return, we have to cast. Get the exit code. Right? So it's that easy to add a variable and have the different states set the variable to be different values. So now when I run this program, we see that, I haven't fixed all the code. So this code didn't need to change. That's good. So that's how you write your program, right? This is a really important part. You've worked out all your states in your state transition diagram, and now you're just going to express them in code just with names. So you have to do your number defines. You have to set up this table to say I can move from this state to this state, and when that happens, call this function. And then you just have to make functions that return int and take an environment pointer. So how does the finite state machine itself work? It's stupidly simple. Here's the run function. We have an initial set of states, right, that we're just going to copy over. Some of these persist. I could probably look at this and see if I could make one of these variables local. I'm not sure yet. I went through a few iterations of this. And we're going to grab our function. So perform is done by finding that transition. That transition thing is this. Init to start, or start to A, or start to B, or A to end. Right? So we're going to use these start and the from and the to states, which are just ints. We're going to use those to find the function in from that list of that array of transitions to find the function we want to call. And we'll worry about that code in a second. Then we're just going to set up the environment to say you're moving from this state to this state. I have no reason not to provide some information, so I figured that's good information to provide. And then I reset our from state to be the one that we were coming from, right? The to state will now be, once we run the whole thing, the to state will become the from state. And we call perform, which means we're going to call one of these functions down here, and it's going to return the new state to go to. Okay? So then what's going to happen is we're going to call perform again, right? Because it's in a loop. We're going to call perform. So the first time we move from init to start, so we came in here, we grabbed that function, we grabbed the start function. We set up the environment, we set up the part of the state we called perform, which means we actually called the start function. The start function then returns either A or B, depending on what that value was. So it returns A. So our to state ID is A, and our from state ID is start. So we have start and A, which means when we go through this transition thing, it's going to, again, loop through all this, and it's going to find start and A, and then it's going to call the A function. And the A function is going to return A and end. Right? The A function returns end. So we're going to move to that one. And then end is going to exit the whole program. So that's how we can move through states. That was part of code that didn't work. So this is a code that could be made slightly simpler. Or sorry, not simpler, faster. But I would argue with you that it's probably not worth it. So all this does is it grabs the first line, the first entry in that table, and it's going to loop over them one at a time and check to see if it has a perform function. If it doesn't have a perform function, if it's null, we're done. So that's why you want to make sure that you don't have null inside of any of these functions here, because it'll never go to anything past that. So if it's got a function, it'll check to see if the from and the to, so start from init and start. So the from is init, the to is start. So we're going to find init and start. It happens to be the first one. Great. Then we're just going to return that function. We're going to return the start function. So that's how we get that function. So how could this be made? That's how we get that function here that we're going to call here. So how could we make this code better? Well, imagine you had hundreds of states. You probably won't, which is why I think it's not worth it at all. You're probably not going to have a huge number of states. So looping, what happens is every time you're going to change states, it has to loop through the entire table. A better way to do that is with a hash table. Because it can directly go to the right entry, basically. But if there's not that many entries, it's probably not worth the hassle. But you could go ahead and write a hash table to hash on the from and the to IDs and make it faster. You won't have to loop through the whole table then. The size of the table won't matter. Your choice. I didn't feel it was worth it, and it's a lot more code and harder to follow. So I was keeping things simple. So that is the program. So let's see it running. So we went from we went to the start function with the ID of 0 from state and 1 to state. We went from init, which is 0, to start, which is 1. Start then went to the A state, which means we went from 1 to state 2. And then 2 went to the end state, so end was called from state 2 to state 4. So that information there is useful if for some reason end needs to know if it came from A or B. You probably don't want to do that, but you could. It's there, so why not provide it in case somebody does have a use for it. And then if we change this to false, the only thing different is we went from 1, and instead of 2, we went to 3, with 2 being A and 3 being B. So it really is that simple. There's a couple of tricks. If you want a function to call itself sort of thing, so when we move from start to B, we call B, and we could add another function. We could add another thing here. B can also move to B, and it would call B. So you can have a recursive call that way. Or it's not quite recursive, but you can have a state re-enter itself just like that. It's not a problem. You just have to have a case where the B function returns and B or error, right? So it could return any one of those 3. The flaw that I just realized, well, actually, it is a flaw. I should check for it. I don't actually check to make sure here that if perform equals null, we have a problem, right? So we should do an assert, and I'll put that in before I publish the code. An assert isn't the right thing either, so I'll show you how to. Well, I can just exit with an exit failure. And we can do a. So if they couldn't, if there was an impossible state transition, like we wanted A to go to B, and that's not a state that we actually allowed, but somehow something screwed up and wound up returning that, now the perform function will be null. We will exit out, print out that we can't find it and exit out of it. So we'll find the bad state. Assert is good. The problem with assert, if you don't know what it is, assert just checks to see that conditions are true. The problem with assert is that you can turn it off by compiling versus debug versus release. Compile debug, your asserts are left in. If you compile with release, they're taken out. A friend of mine who's a really good programmer said, I took the time to write those asserts. I actually want them to be there in forever. So I don't use assert for that reason. So I can go with that. But that is the way that you can have a state call itself. You can just say B goes to B, and it calls B, and now you've got a state that will call itself. If we think of this in terms of an HTTP server, here's the kind of thing I would do. I'm not going to code it up, but I'll give you the lay of the land. So init, that just means, this would be always my initial thing, because I'm always going to move from init to start. So init would be a pseudo state. It doesn't actually exist. It's turning the power on. You can never go back to init. Well, I guess technically you could go back to init. There's nothing stopping you, but you wouldn't typically go back to init. So we go from init to start. At server start, we're going to have to do things like parse our command line arguments, and we're going to have to do all that kind of stuff. So start might move to a state of listen. Listen would set up the socket to do accept on, and we won't worry about threads or processes and all that. We'll just pretend it's a single threaded, one client at a time. So we'd put the file descriptor in here. We'd add another variable here for the file descriptor. And that's what we would call accept on for that file descriptor. So listen would just sit there waiting to accept a call. Once it accepted something, it would return, and it would return a state of like, call read. So read would then read the request from the client, and it would set that request into a variable here, string copy it in, and malloc and string copy whatever, and then it would return to another state of process request. Process request would then figure out what kind of request it was. It could go off and read from the hard drive, all that fun stuff, and return and store anything else inside the environment, and then return another state of send response. Send response might need to know some information about the request, like was it a head or was it a get? Because one of them has to send the data, one of them doesn't. So depending on what you're doing, it could do a different kind of state, right? You could have reply head, reply state, reply get. There's various ways you can handle that. And then once the response had been sent, the next state is going to be going back to listen, right? Which is going to just accept the next request, kind of thing. So that's if you think in terms of an HTTP server, it becomes pretty simple. You've got just this little bit of code, and the finite state machine handles all the moves between things, and you use the environment structure to communicate between the different states. A variation that I just took out because I didn't see the benefit of it anymore was these used to actually be, instead of functions, they were structs that had functions. And my initial idea was that I would store these variables inside of those structs, so each state had its own variables, but that didn't wind up being practical for reasons that you could only pass a variable from one state to the next. I'd rather be able to just have the state persist for the whole thing. So this is almost like a set of global variables, honestly. But there you go, it's that simple. So you can now express a state transition diagram as just a series of states and the code to execute for that particular state. And each state can move on to the next state. And we'll talk more about what you're going to do with this next class.